All right, this is section 22.2, and we're going to take it in well, we might do it all in one part, just depends on how long we're going to take to go through it. This is called using electrical energy, but it would be better thought of as some principles about electrical energy as it flows and how we measure electrical energy. So we're going to start in section 22.2 by reviewing something. Power is current times voltage. Voltage is current times resistance. If I put those two together, if I simply take that IR right there and put it right in there, I get an interesting equation. I get that power is I times IR, or power is I squared R. Same equation, just redone. We've done that many times where we work with an equation. By the way, we could also do the same thing and write that I is V over R. Plug that in here and you would get this equation as well. But I will tell you from experience, it's this one that we're going to end up using most of the time. Power then is directly related to the resistance and the square root of the current, or the square of the current. Now that's important because the resistance, say, of a wire doesn't change. And that means that the higher the current, the more power you're going to need. You might say, well, that's true here of voltage as well, but stay with me on this. The higher the current, the more power it's going to take, the more watts it will be. Now, there's one other equation, and that is that energy is power times time. And that means that energy can be thought of as IVT, where T stands for time. I know for those of you in calculus, that looks like intermediate value theorem, but that's current times voltage times time. But we could also use this equation, I squared R times T. In other words, if I was to take and send an electrical current through a wire, and that wire has resistance, and I send it through for a certain period of time, there will be energy that will be used in that process. Most of the time, that energy ends up as heat. If you've ever taken an electrical wire and felt it, when electricity is going through it, it gets warm. Now, sometimes we put insulation on there. I remember years ago, I had a coin in my pocket. I think it was like a quarter. And I had a quarter, and I was carrying around a 9-volt battery. A 9-volt battery is the little one that has the positive and negative ends on the top. Most batteries, it's on opposite ends. And I had that in my pocket, and all of a sudden I noticed my pocket was hot. And that's because the electricity was flowing through the coin, generating heat. All right? And that'll be one of the types of questions that will get asked in the homework this evening. They will tell you something like this. You've got a 20-watt circuit, and it runs for 2 minutes. How many joules? Well, energy is power times time. It's 20 watts, which is joules per second, times, we'd have to change this to 120 seconds, and this would be 2,400 joules. If they gave me a circuit and they said I've got a 12-volt circuit and I've got, let's just say, a 20, we're going to make life easy for ourselves, a 24-ohm resistor, and this is going to run for 1 hour, how much energy is used, and for the most part, how much thermal energy, how much heat is produced, because that's really all a resistor does. A light bulb gets really hot because most of the energy is turning into the old-fashioned incandescent light bulb. Most of the energy is turning into heat. Just part of it is in the visible spectrum. So first thing I would have to do here, well, I could use this equation, but we're going to use this one. The power here is voltage times current, or I could find out current by doing volts divided by resistance, but this is, oh, I don't know what I'm sorry, I don't know what my power is yet. So first thing I have to do is find my current. Current is voltage divided by resistance. 12 volts divided by 24 ohms is 0.5 amps. And now my energy will be I squared R times T. And I squared then would be 0.5 amps squared times 24 ohms. Oops, 24 ohms times 1 hour is 3,600 seconds. And we would get 0.5 squared times, oops, clear that, 0.5 squared times 24 times 3,600. And 21,600 joules, or 2.16 times 10 to the 4th joules. Okay? Now, when we work with electricity, and especially when we have a generator which puts out large amounts of electricity, the unit for energy that we are going to use is called the kilowatt hour. By the way, a lot of people think that that's power, but if you look at it, kilowatt is a unit of power and hours is a unit of time. And power times time is energy. When you get, if you ask your dad, since you're home, ask him for the last power bill. And the last power bill will say how many kilowatt hours were used. That energy power company doesn't sell you power, it sells you energy. It tells you how much energy you use. Well, how much energy is it? 1 kilowatt hour is actually a lot of energy. A 1 kilowatt, and by the way, the unit looks like this. I did that back. I always do it wrong, but it's a lowercase w, lowercase k, capital W, lowercase h. 1 kilowatt hours would be 1,000 watts times 1 hour, which is 3,600 seconds. And that would be 3, 6, 1, 2, 3, 4, 5. 3.6 million joules is 1 kilowatt hour. 3.6 million joules. If I was to tell you that you have a 100-watt light bulb and it's running for, let's say you left it on all day long, left it on for 8 hours, how many kilowatt hours did that use? Well, we would have to change this to kilowatts. 100 watts is 0.1 kilowatt times 8 hours. This would be 0.8 kilowatt hours that would be used, 0.8 kilowatt hours. Now, if you want to figure out how much that is in terms of energy, this then would be 3,600 or 3.6 million joules for every 1 kilowatt hour, and 0.8 times 36 is 28.8 2.88 times 10 to the 6 joules. Interestingly enough, when you do work with kilowatt hours, generators are so much more efficient to create electricity than batteries, that you can take and buy this amount of energy usually for somewhere around a quarter. So right now, electricity rates are somewhere between 0.25 cents, 0.25 dollars, 25 cents, I'm going to do it this way, 25 cents per kilowatt hour. Or sometimes it goes up to 50 cents in California. California is actually quite expensive. So let's take this same problem I just did. Let me erase this here. And let's say you did run a light bulb. You had a 100-watt light bulb. You ran it for 8 hours. And your cost for electricity is 25 cents per kilowatt hour. How much did you spend? Well, we have 2.88 times 10 to the 6. We have 0.8 kilowatt hours times 25 cents per kilowatt hour. And that would end up being 0.8 times 25. I should be able to do that in my head. About 20 cents. Not much, but about 20 cents. All right, my computer looked like it turned off and I was just checking it. Now, we are going to do some problems on there, but before we do that, I just want to mention one interesting thing. It'll be in your book, and it's just a curiosity. When you go back to this equation, energy is I squared R times T. There's an interesting thing that will happen, and then this one as well, P is equal to VI. In order to transmit electricity from, say, Hoover Dam, which is in Nevada, 500 miles across the desert to Los Angeles, how are they able to do that without losing so much energy? In other words, that's a long distance, and there's a lot of resistance. And why is it that they're able to be able to transmit all that? We don't even think about it, but there's hardly any losses. Well, what happens is this. Voltage and current are inversely related. If I raise my voltage, I drop my current. And so what they will do is they will raise the voltage, sometimes close to 1,000,000 volts going across the desert. 1,000,000 volts. And what that does is that drops the current way down. Let's just for numbers say that we were working with 1,000 watts. By the way, it would be more than that, but 1,000 watts and 1,000,000 volts. And we divide that to find the current. All right, 1,000,000 on each. And this will be 1,000th, 0.001. 0.001 amp. Now watch what happens. What happens if you square 0.001 amp? Well, it becomes 0.000001 amp squared. And this is so tiny that we have very little energy losses. So at Hoover Dam, they're going to produce electricity. They'll produce a voltage and a current. Then they use something called a transformer, steps the voltage way up. The current goes way down. As soon as this current is less than 1, squaring it actually makes it smaller. And then because of that, we can transmit energy across the desert or long distances. Doesn't have to be across the desert, long distances. And the amount of loss of energy is very, very low. By the way, then they get it into the city, into Los Angeles, and then they take the voltage and they lower it back down for shorter lengths of transmission until we get outside of your house, and they go from about 10,000 volts down to 100 volts, and then you have the right amount of current. So high voltage or high current and voltage, then we step the voltage way up, drop the current, take that all the way across the desert, and then bring those back close together and then switch them when they come into your house. So you have relatively low voltages comparatively and high currents. But it all comes about because of this equation. So what we're going to do on this section is problems 23 through 31, the practice problems. And let me give you the answers for the evens. 24A is 1.2 amps. 24B is 16,000 joules. 26A is 20 amps. 26B is 13 13,000 joules. 28A is 1,800 watts, or 1.8 kilowatt. 18B is 270 kilowatt hours. And 18C would be $32.40. And problem 30, the answer is 9.5 hours. So that's lesson 2 for this week. And try those problems and we should be in pretty good shape. So I will hopefully see you soon after Easter, maybe a week or 2 after Easter, the way it's looking, but I'm looking forward to seeing you guys again. All right, we'll close the video off at this point.